Okay, so this is a quick pump operations overview. We're going to start off with our emergency evacuation signal. If an OIC orders an evacuation, we are to give 5 quick blasts of our horn, wait 5 seconds, give another 5 quick blasts, wait another 5 seconds, and give a third 5 quick blasts for a total of 15 blasts to inform the interior crew that there has been an emergency evacuation ordered. Some things to think about as a driver when we're leaving the station or leaving the scene. Helps to do a quick visual 360 of the vehicle. Before we leave, we want to know where we're going. Our officers have a job to do, so we should be able to do ours without asking them. Drive with caution. This isn't just to avoid accidents, but also to take care of our vehicles. They're very heavy and they're big, and if we drive them around like cars, it will cause problems. Vehicle placement when we're arriving at a scene. We want to consider hydrant locations. Consider if we're going to forward lay, reverse lay, leave the front of the building for the ladder if possible. We're going to need to leave room between the apparatus. It should be at least a half of a vehicle length in case we need to pull ladders or something out of the back. And then also consider traffic control depending on what type of scene we're at. Putting our vehicle in pump when we arrive on scene. We obviously want to pull our emergency parking brake first. We're going to shift our gear into neutral, move the road to pump lever from road to pump, pausing in the middle for a second, shift our gear back into drive. Indication that we went into pump would be our RPMs, we'll hear them increase. When we exit the cab, we want to chalk our wheels, at least the rear. Open our tank to pump. If we need to prime the pump, we'll do that then. And then crack our tank fill and or our pump recirculate. When we deploy our hand lines, as an operator, we want to know the length of the hose, the size, what nozzle's on it. We want to make sure our hose bed is clear of all the hose before we charge the line. Our first priority is getting the attack crew's water. We have plenty of water in our tanks. If we can get them their water first, then we will establish a permanent water supply. Once we get our permanent water supply, we can let our OIC know that we have that. The difference between your tank to pump open and closed. Once we establish water from a hydrant, we can leave our tank open, tank to pump open. By doing this, if something happens to our permanent water supply, we will start pulling water from the tank without any interruption. If we close our tank to pump once we get a permanent water supply, there will be an interruption in water if something happens with our main water supply, and it will be up to us to open our tank to pump to start pulling water out of our tank again. This is up to the operator, how they like to operate, but what I have heard is closing your tank to pump just assures you that you always have a backup water supply. If you do leave it open, just be aware that you can start draining water out of the tank without knowing. Cooling the pump, you can avoid overheating the pump by keeping your pump recirculate valve open or cracking your tank fill. The pump recirculate valve should always be open anyways, but cracking the tank fill is a good way to circulate water. Also, you can open a discharge valve if you're on scene for a prolonged period of time and your pumps are running, or your pump's running. By taking water and flowing it out an outlet gauge, you are replacing fresh water from the tank or the hydrant back into the pump, which will essentially cool it. One way to check if it is overheating is just putting your hand on the Harrington. It will get hot, and then you know you need to start recirculating water, or you're not recirculating enough water. This is a picture of our pumps. Water enters the impeller. The impeller spins, and centrifugal force creates our pressure. Our pressure is built up in our discharge valve and goes to all of our other valves and outlets in our pump. All of our pumps are single stage. Once we get water and we need a hydrant, or once we get our lines in place and we need a hydrant, our procedure is to place our gate valve on the 2.5 outlet of the hydrant, flush the hydrant through that gate valve, close the hydrant gate valve and the hydrant. We're going to connect our Storz adapter to the 5-inch, and then we are going to open our 5-inch fully. Make sure that the hydrant is fully open so we have the full capacity of the hydrant giving us water. Our hydrants in our city, the 5-inch is Cleveland Standard. The 2.5s are Cleveland Standard thread. All of our hose and our nozzles are also Cleveland Standard, and all of our 1 3/4 hoses and nozzles are National Standard. Just be familiar with the adapters that we have on the vehicles. If we do go to Lake County, they use National Standard with their 2.5s, so we would have to use an adapter. Our residual pressure gauge is going to read the pressure that is coming into the vehicle. If we get below 20 psi, we are to notify our OIC. If we get below 10 psi, we are in danger of damaging our water main. Our pump discharge gauge is going to read the pressure of water being discharged from our pump. When we're in pressure mode, the governor will adjust the RPMs to maintain the set pressure. So if we set our discharge at 100 and we introduce hydrant water to the pump, our pump will adjust and keep us at 100 psi. If we open lines and we need more pressure, our pump will automatically increase the RPMs and keep us at 100 psi. In RPM mode, we set our RPMs, and based on water coming in or water leaving, our pressures will fluctuate. We will just keep the same RPMs the whole time. We don't really have to worry about RPM mode because we always pump in pressure mode. Our outlet gauges read pressures at our outlets. The outlet gauge should read the same or very close to the same as our discharge gauge when everything's closed. Once we open a line, it can read as much as 20 psi difference, and it would be lower. So when we're gating back a hand line, we're going to open our outlet slowly while the nozzle is flowing water. If the crew is not flowing water, then our outlet gauge is always going to read whatever our discharge gauge says. Once the line is opened, then your outlet gauge will read differently than your discharge gauge. If we want to gate back, the only way to gate back is to do it while you're flowing water. As soon as the crew shuts down their line, your outlet gauge is going to go right back to whatever your discharge says. Our optimum nozzle performance for our smoothbore hand lines is 50 psi. Our smoothbore master streams is 80 psi, and our fog nozzles are there's a rating on them. We have 50 psi fog nozzles and 100 psi fog nozzles. So check your nozzle to find out what the rating is. These are our friction loss constants as an operator that we need to know. 5 psi per floor. We're going to add 25 psi for our master stream appliances, and we're going to add 25 psi for our standpipe. This friction loss calculation, first off, this is not a friction loss class. We just put these in here just to explain how we came up with the pressures that we came up with. So that being said, just a real quick overview. This is the calculation that NFPA will have in their handbook. This is suggested how we figure out our friction losses, and the only variable in this calculation is the coefficient of the friction. NFPA gives you your coefficient for 1 3/4 line and 2.5 line, and I will explain in a second. So I'm just going to read this. NFPA Fire Protection Handbook suggests using a coefficient of 15.5 for 1 3/4 hose and 2 for 2.5 hose. These numbers have been found to be high in relation to newer and more efficient hose construction. Using these coefficients in our friction loss calculations are causing us to overpressurize our hand lines. Our friction loss chart was based off our hose coefficients. Then it was checked with inline flow meters and pitot gauges to ensure it is relatively accurate. So when we contacted the hose manufacturer, the coefficients that they want us to use for our 1 3/4 line is 9 and 1.5 for a 2.5 inch line. Once we find our friction loss, all we do is add our friction loss with our nozzle pressure, and that gives us what we should pump our outlets at. So this is just wrote out for us. When we're using the coefficient of 15.5 that NFPA recommends, when you work it all out, it will tell us that we get 93 psi friction loss for 200 foot of 1 3/4 hose at 175 gallons a minute. This is our Mattydale, and when we use 9 as a coefficient, which the manufacturer suggests us using, and we have found to be more accurate, it will come out to 54 psi friction loss for our Mattydale. So when we add the friction loss of what NFPA suggests to our nozzle pressure, NFPA would suggest us flowing our lines at 140 psi, and we all know that when we flow a Mattydale at 140 psi, it's way too much pressure, it's too hard to handle. So with the coefficient that our manufacturers tell us to use, we have 50 psi friction loss with our 50 psi nozzle pressure, which gives us 100 psi. This is what we flow our Mattydales at. We get 175 gallons a minute out of the nozzle. We have 50 psi at the tip, which we're supposed to with this setup, 100 psi at the outlet. We went through all the work of the 2.5 also. Obviously the results are closer because instead of using 2 as a coefficient, we're using 1.5, so 25 psi compared to 18. So for our setup with our hose and our nozzle, 20 psi friction loss plus 50 psi nozzle pressure would give us 70 pressure outlet. So our 2.5 Mattydale, we should be pumping at 70 psi. This is a friction loss chart based on our hose. Our 1 3/4 side, we have 10 psi friction loss for 100 gallons a minute, 20 psi for 150 gallons a minute, 30 psi for 200 gallons a minute. So at 175 gallons a minute, which our nozzles are rated at, we do 25 psi per 100 feet. That gives us our 50. Our 2.5 inch hose, this is using the coefficients that our hose recommends. For 250 gallons a minute, we have 10 psi friction loss per 100 feet, and 300 and 500 gallons a minute. And the 500 is on there for our master streams. Just another explanation of our 1 3/4 friction loss. At 100 gallons a minute, we have 10 psi friction loss, 150 gallons a minute, 20, and 200 gallons a minute, 30 psi friction loss. This is our Mattydale setup. We have 200 foot of 1 3/4 hose with a 50 psi fog nozzle. We pump it at 100 psi outlet pressure. That gives us our 175 gallons a minute. This is our frontline Mattydale nozzle. It's a fog nozzle. 50 psi gives us 175 gallons a minute. 25 psi friction loss per 100 feet that we showed you on the friction loss chart. This is our zero torque nozzles, which would be found on our backup apparatus. We are pumping them exactly the same, 25 psi friction loss per 100 feet It's got a 15/16 smooth bore, and we get 185 gallons a minute out of it. There is a fog nozzle on this. It is rated at 135 gallons a minute at 100 psi. This is not to be used for fire attack. And then we also have an adjustable gallonage fog nozzle. These are to be set at 150 psi for 1 3/4 inch. They are 100 psi nozzles, and we have 20 psi friction loss per 100 feet at the 150 gallons a minute. So if this nozzle is on our line, we're going to be pumping at 100 plus your 20 psi per 100 feet. So with a 200-foot line, you're going to pump at 140 outlet pressure. Our 15/16 smoothbore nozzle, this is rated at 185 gallons a minute at 50 psi. These are on our apartment packs. 50 psi friction loss per 100 feet. This is our apartment pack setup. Like I said, we have a 15/16 smoothbore on our apartment pack. If we deploy all 200 feet in an apartment, we are pumping at 135 psi. That is plus 5 psi per floor, and that's going to give us 185 gallons a minute. Just a real quick, when we set up an apartment, or when we set up for an apartment fire, we want to get our first 2.5 inch line hooked up as quickly as possible, get a permanent water source, and get water into the system and charge the system. At that point, once we get the system charged, we want to get our second 2.5 inch line connected. And another quick caution that standpipe systems are only tested at 200 psi once every 5 years. Whether or not this is done, it's just so you are aware that these systems are not tested at high pressures, and when we get to high elevations and we're supposed to be putting in high pressures, just to be aware that you can break things if you don't take your time pressurizing the system, and I would be cautious of going over 200 psi. Our 2.5 inch hose roll, this is our friction loss chart for our 2.5 inch, 10 psi for 250 gallons a minute. This is our 200-foot Mattydale of 2.5 inch hose with our 1 1/8 smooth bore. We pump at 70 psi. This is the nozzle that is on our Mattydale for our 2.5. We have removed the 1 inch tip. The 1 inch tip is almost the exact same size as our 1 3/4 inch tip, and there would be no reason to use a 2.5 inch line if you're going to be getting the same amount of water as you'd get from an 1 3/4 inch. So the smallest tip we'll use with our 2.5 is an 1 1/8. That's going to give us 266 gallons a minute, and we have 10 psi friction loss per 100 feet. So that's where we get the 70 psi for our Mattydale. And if we need more water, we could take the 1 1/8 inch tip off. That'll leave us an 1 1/4 inch tip. That gives us 328 gallons a minute. And because there's more water, we're going to have more friction, so we will pump that at 90 psi, 20 per 100 feet. So you have your 40 plus your 50 at your tip, which is going to give us 90. We do have an adjustable gallonage 2.5 inch fog. This is a 100 psi fog nozzle. We have to set the adjustable gallonage to 250 gallons a minute, 10 psi friction loss per 100 feet. That is 100 for your nozzle plus 20 psi friction loss, so you pump at 120.